This is video number 1 on formulas of the topic refraction of light. Timestamps are given in the description box. You can watch parts of video if you are running short of time. In this video, I will discuss formulas related to laws of refraction, Snell's law, refractive index, and image formation by spherical lenses. Refraction of light is the bending of light when it passes from one medium to another medium. Here, light is passing from air to glass. This is the normal at the interface. The light ray makes an angle of incidence I1 to the normal. Once it enters the glass, the speed of the light in glass, say V2, and the speed of light in air, V1. V2 is less than V1 because glass is a denser medium. So the light will take a shorter path, that is, it bends towards the normal. And again, when it comes out and goes to air, the speed here is more, so it will take the longer path, which is bending away from the normal. So the amount of bending inwards and the amount of bending outwards will match, so that the emergent ray and the incident ray are parallel, and this is called lateral displacement. This is the incident ray, this is the refracted ray, and this is the emergent ray. So the bending of the light when it changes medium is called refraction. Laws of refraction: the incident ray, the refracted ray, and normal at the point of incidence are in the same plane. This is the incident ray and this is the normal at the point of incidence. The interface between air and glass will be like a surface like this. So the incident ray will hit this surface at some point. Wherever it hits, we can draw a normal. Normal can be drawn at any point, but this normal is drawn at the point where the light ray goes and hits this interface. So the incident ray and the normal will form a plane, and let this be the plane of the board. So the refracted ray can make an angle R1 with this normal anywhere like this, but this first law states that this refracted ray cannot be in any plane, but should be the same plane formed by the incident ray and the normal. Second law of refraction: the ratio of sine of the angle of incidence to the sine of angle of refraction is a constant for a given pair of media, that is sin A by sin R is constant. Here, if the angle of incidence is increased, so we can expect the refracted ray angle should also increase. So I increases means R will increase, and I will change from 0 degrees to 90 degrees. So in that case, when I increases, sine of the angle I will also increase, and also sine R will increase. It turns out that the sine I and sine R are proportional. That means the ratio sine I by sine R is constant, and this constant value is a given number for a given pair of media. This is found out by Snell, so that's why it's called Snell's law. Refractive index for a given pair of media. So the velocity of light in the first medium V1 and the second medium V2. If it is denser medium, V2 will be less than V1. So this ratio V1 by V2 and the refractive index of second medium with respect to first medium. So refractive index is defined like this: the ratio of the velocities, and if the second medium is denser, like here, this thing will be greater than 1. So this thing should also be greater than 1. So it should be velocity of the light in the rarer medium, which is air, to the velocity of light in the denser medium, which is glass here. So 2, 1 is defined as 1 by 2. And also when light comes out here, refractive index of the air with respect to glass, this will be less than 1. So this ratio of the velocity of glass, velocity in the glass by velocity in air. This is less than 1, this is also less than 1. And diffraction index of air with respect to glass and diffraction index of glass with respect to air are related as reciprocal, because the ratio of the velocities, light is starting from here to here, this ratio is v1 by v2, first velocity, second velocity. Here the refraction index of the second medium with respect to the first medium is v2 by v1, so it's a reciprocal. n21 and n12 are reciprocals. That is the ratio of the speed of the light in the two media. Spherical lens is formed by taking two spheres and make them intersect and just keep this intersecting part. That will give me convex lens. Two glass spheres, make them intersect and keep this intersecting part, that is convex lens. Concave lens to make concave lens, take some chunk of glass and make two spherical voids, non-intersecting voids. This void. So here it is glass. In this glass, remove this amount of glass in form of a sphere, and this is also void. And take this glass here in this middle portion, and this much of glass you retain, and remove all the other glass. So that will give me concave lens. So basic thing is, this surface is a part of a spherical surface, and also this is a part of a spherical surface, even these two. But this is formed by intersecting spheres. This is formed by creating spherical voids which are not intersecting, and this concave lens is the part which is in between the two spherical voids. So this will have an axis of symmetry, which is the line joining the two spheres. Here the axis of symmetry is the line joining the two spherical voids, center of the two spherical voids. So this axis of symmetry, this one, that's principal axis. The lens is symmetric about this axis. So this concave lens is symmetric about this axis, which is principal axis. To get principal focus, send a parallel beam of light which is parallel to this axis, and after refraction it will converge at one point. That point is a focal point. For a concave lens, the parallel beam, after coming out, they will diverge. This is divergent rays. They will not meet on the right side, but projected backwards will appear as if it is starting from a point. So it will appear as if all these rays are starting from this point and going out. So this is a focus, and it's a virtual focus. Convex lens is called converging lens because it converges the light rays after refraction. Concave lens diverges the light rays after refraction. So special rays, these rays are helpful to figure out the images of object. So the first special ray is a ray parallel to the principal axis after refraction will pass through the focus for convex lens. For concave lens, it will diverge, but it will appear to start from a point on the principal axis, which is the focus. So this is the first special ray. Second ray, it's reverse of the first one. A light ray passing through the focus after hitting the lens comes out parallel to the principal axis. Concave lens, a light ray appearing to hit the focus after refraction will come out parallel to the principal axis. First ray, the path of the light ray can be reversed. So the light ray sent in this direction will come out in this direction. So light ray passing through focus after refraction will come out parallel. Here also, light ray appearing to hit the focus after refraction will come out parallel to the principal axis. That is the second special ray. Third special ray, this lens will have a center. So light ray passing hitting the center will go undeviated. It's as if the lens is not there. That's true for even for a concave lens. Light ray hitting the optical center, which is the center of the lens, will go unaffected without any deviation. So using the special rays, one can figure out the images of different position of the object. So this is a convex lens. Start with object at a far away distance, say at infinity. So from infinity, the light rays that will be coming are parallel light rays. So these light rays after refraction will pass through the focus. So after that, bring the object from infinity to somewhere nearby beyond 2f. Second case. So take a special ray, parallel to the place after refraction pass through the focus and go straight. And second ray, special ray, hitting the optical center will go undeviating. So these two light rays from A meet here. So the image of A is A prime. There are a lot of rays coming out from A, like this ray. So this will also go and meet here. So all the light rays which come out from A will go and meet here at A prime to give the image of A. But these two rays are special rays, so it's easy to draw to figure out where it's going. But these are not special. These are some arbitrary rays. So if this is the red spot, there will be a red spot here. Similarly, take this middle point, say A1. The image of this one will come here. Suppose this is red. Red will appear here. And suppose this middle point is blue. The middle point here will be blue. So the image is getting inverted. One more thing to notice is the object, the image, which is at focus here, which is a point image. Here it's moving away. Next is move this object to 2f. So the image will move further. Object is moved to 2f on the left side. Image is moving to 2f on the right side. Here the size of the object and size of the image are same. Here also two special rays parallel will pass through focus. Through the center will go undeviated. So these two rays are made here. Next, to move the object here, that's between 2f and f, in this case. So here again two special rays pass through the focus in this one. So you can see as the object is moving in, the image is moving out. And also, the image of the size is getting bigger. So whichever is far away, that is bigger. Initially the object is far away, so the object size is bigger. Once it comes nearby, at 2f both the sizes are same. After that, image is far away, so the size of the image is moved. And still we can move the object from here to here at the focus. For this, we get parallel rays. So the image is moving to infinity. Here it's a finite distance. As you move further, it's still moving away. Next is to move the object from here to here between the focus and the optical center. So now we get divergent rays which will not meet. So if you project it backwards, it appears to start from a point A prime. So looking from this side, it will look as if these light rays are coming from this image here. So this is a virtual image. So firstly, we have a real image. At the focus, the image is going to infinity, and within the focus, it's a virtual erect image. So these results are summarized on this table. Position of the object starting from infinity is moved inside infinity and then beyond 2f, at 2f, between f and 2f, and then at focus and between the focus and the lens. So at infinity, the image is forming as a point object at the focus. Beyond 2f, it's having between f and 2f diminished size, and at 2f, the image is forming here 2f on the right side. So here, both are the same size. Before this, the object is a greater distance and of a greater size. After this, the image is nearby, object is nearby, and the image is far away, and whichever is far away, that will be size will be moved. So between f and 2f, image is enlarged. And at focus, the image is formed at infinity, and moving close to the lens within the focal length, we will get divergent rays So there won't be any real image, but we'll get virtual image, and which will be erect. So first 4 cases, it's producing convergent rays, which will have a real image. Last case, it's producing divergent rays, which will produce a virtual image. This 5th case, it will produce parallel beam of rays, which will not meet at all. Similarly, for concave lens, there are 2 cases. Object is a large distance, say infinity. Parallel beam of rays after refraction will diverge, but it will appear as if all these divergent rays are coming from a point object located at the focus, which is the virtual focus. After that, if we move the object to any finite distance, does not matter whether it's 2f or f or close to this one, the situation is same. You always get divergent rays. Parallel difference after refraction will go like this, so that it appear to start from the focus. The optical center will go straight, so this thing projected backwards. So these 2 light rays 1 and 2 will appear to start from here. So the image of A is A prime there. So we take a middle point A1, it will appear to start from here, the divergent light rays. So now here, if we try to move the object inside, the image will also go closer to the lens. For a virtual image, the property is if the object distance decreases, image distance also decreases. So this is summarized in this table. Object position at infinity and at a finite distance. So infinity image is at a virtual focus, it's a point size image. After that, at a finite distance, it's always between the focus and the optical center. It's a diminished image, which is virtual and erect.